Hello, everyone. To those of you who don't know me, my name is Ido Galil, a master's student who just moved to the direct PhD track and under the supervision of Ran Elianiv. Today's seminar will have two parts. In the first part of this talk, I will present a comprehensive study that evaluates the uncertainty estimation performance of 484 deep ImageNet classification models that has helped us identify numerous and previously unknown factors that affect uncertainty estimation. I did this study together with Muhammad Dabakh. In the second part of this talk, I will present a novel adversarial attack targeting uncertainty estimation from the paper Disrupting Deep Uncertainty Estimation Without Harming Accuracy, that is to be published in NeurIPS 2021. If anyone has any questions during the presentation, please wait until the end of the talk. I will leave some time for questions. So first, let's get some background. Should we even care about uncertainty estimation? When deep neural networks are used for applications with low tolerance for risk, such as medical applications, in which incorrect predictions could mean life or death, they must employ an uncertainty estimation mechanism to better manage their risk, such as selective prediction, a method that I will explain now. In this example of 2 cats and 2 dogs, the model classified correctly 3 out of 4 instances, which means it provides us with an overall accuracy of 75%. But this might not be good enough for us. How can we use uncertainty estimation to improve our performance? There are various techniques for estimating a model's confidence, but in this talk, we will focus on softmax response, which is the maximum softmax score of the prediction vector. Confidence scores tend to rank correct predictions higher than incorrect ones, as demonstrated by this histogram of confidence scores of correct and incorrect predictions made by an EfficientNet on the ImageNet dataset. We can use this fact to set a threshold on the confidence scores and abstain from making predictions for instances whose confidence is lower than this threshold. Here, we set our threshold score value at 0.6 and abstain from making predictions from any instances with lower confidence. This causes our classifier to abstain from predicting the dog with the glasses as a cat and leaves us with a selective accuracy of 100% for a 75% coverage. Coverage simply means the percentage of predictions that the model has not abstained from. Here, the model has not abstained from predicting for 3 out of the 4 images, therefore our coverage is 75%. Notice that we were able to achieve this outcome because the model has ranked all correct predictions higher than the incorrect prediction. If the model were to rank worse, either the selective accuracy or the coverage would have become worse as well. For example, here the incorrectly predicted dog was ranked higher in terms of confidence than a correctly predicted cat. Therefore, for a 100% selective accuracy, the largest coverage we can get is 50%. If the incorrectly predicted dog were to be ranked above all other predictions, we would not have been able to reach 100% selective accuracy at all, no matter the coverage. So perhaps getting good selective performance when classifying cats and dogs doesn't sound too exciting. Instead, let's explain the motivation by a case in which selective performance would translate into something we all would like to have more of: money. Consider 2 models, A and B, for the stock market that predict whether a stock's value is about to increase, decrease, or remain neutral. Knowing which stocks we should invest in could help us make a huge profit. Suppose that model A has a 95% true accuracy and gives a confidence score of 0.95 on every prediction, no matter if the prediction is correct or incorrect. If we invest according to this model's prediction, 95% of the stocks we invested will generate profit. This sounds pretty good, doesn't it? However, we will lose any money we have invested in the 5% that were incorrectly predicted. Model B, on the other hand, has only a 40% true accuracy, but always gives a confidence score of 0.6 on correct predictions and 0.4 on incorrect ones. This means we could set our selective threshold at 0.5 and get a selective accuracy of 100%. If we invest only in these stocks, we will always make a profit. This sounds even better than Model A. So even though Model B has a significantly lower overall accuracy, it is still much better for the purpose of investments. So one way we can understand a model uncertainty estimation performance profile is by looking at its risk coverage curve, also known as an RC curve for short. This is a graph showing the risk we get for any coverage of instances we require the model not to abstain from. In practice, it means we iterate over all different thresholds we can set, such that the coverage will match the coverage required. The risk here is simply 1 minus the accuracy, since we use a 0-1 loss. This is an RC curve for a ResNet 18 I trained on CIFAR 10, by the way. So let's see a few examples for how to read this curve. At coverage 1, we reject nothing, and our risk is 0.05, meaning the model's overall accuracy, the accuracy you usually mean when you say accuracy, is 95%. At coverage 0.8, we reject 20% of the instances that we were assigned the lowest confidence by the model. Doing only that brings our selective accuracy to an astounding 99.5% for any instance we have not abstained from predicting. This is also known as selective risk. The selective risk is defined as the risk we get for a certain amount of coverage. So this curve is very informative, but sometimes we want to quantify uncertainty estimation performance in one number. One way to do this is by calculating the area under the RC curve, which is simply the mean selective risk. We call it URC for short. Note that URC has a major drawback, which is its sensitivity to the model's overall accuracy. That is why I will use another metric, UROC, which is the area under the well-known ROC curve when comparing models with different accuracies. So now that we know how to read an RC curve, let's see some interesting examples. The red curve is the RC curve of an EfficientNet model on the ImageNet dataset. It's a pretty good curve. You see that as the model is allowed to abstain from more predictions, the selective risk improves and becomes smaller. The green curve is the curve of a hypothetical model, which gives random confidence scores for all instances. The selective risk doesn't change no matter how many predictions we allow the model to abstain from. This means the confidence scores of such a model don't tell us anything about how likely its predictions are to be correct. Model A from the investment example that we saw earlier that had 95% accuracy but assigned a confidence score of 0.95 for all instances is a good example for a model with such an RC curve. The blue curve is the worst possible RC curve we could get. As we allow the model to abstain from more predictions, the selective risk only becomes worse. It means it ranked all the incorrect predictions higher than its correct predictions. So if we were to ask this model to only please model, let me have your 20% most confident instances. For example, I will have exactly 0% accuracy for those instances. Remember the shape of this blue curve because we will see something very similar to it in the second part of the talk when we present our attack on uncertainty estimation. Another important aspect of uncertainty estimation is called calibration. Calibration refers to the interpretability of the confidence score that the model gives us. So ideally, if we consider a model for predicting the weather, for example, what we would want it ideally to make if it made many predictions for rain with a confidence of 40%, the average amount of times it would actually rain would be exactly 40%. One popular metric to measure calibration is called expected calibration error, or ECE for short. To calculate it, we first take a large sample of predictions made by the model. We then divide them into different bins by their predicted confidence scores. For example, the bin with the red arrow pointing at it contains all predictions with a confidence score between 0.3 and 0.4. Next, we calculate the average confidence of the bin. This average amount of confidence is visualized by the blue filling. So, for example, for that same bin, the average confidence is almost 0.4. Next, we calculate the average accuracy of the predictions for that bin. The average accuracy of the bin is visualized by the red stripe filling. For this bin, the average accuracy is 0.6. A calibrated model would have had an average accuracy of 0.4 for that bin. Therefore, the difference between the average confidence and the average accuracy is the bin's calibration error. ECE is simply the mean error for all bins. While I will not show many results concerning calibration during this talk due to our time limit, it was also studied in depth. So now we understand what is uncertainty estimation and how to measure it. And we may ask, which factors lead to a better uncertainty estimation performance? To identify these factors, we have conducted a comprehensive study that evaluated the uncertainty performance of 484 deep ImageNet classification models. Due to the lack of time of this talk, I will not be able to go over all of our discoveries, but instead will give some of our highlights. In this slide, we see a comparison of RC curves made by 3 different models. The blue and green curves were made by vision transformer models, VITs, that trained differently from one another. This means they are of the same architectural family, but are significantly different in their overall accuracies due to their different training regimes. The red curve belongs to an EfficientNet V2, an extra large version of it with a very large amount of parameters. The most important takeaway from this comparison, in my opinion, is that a model's overall accuracy is not a good predictor of its selective accuracy. To understand why, let's focus on the green and red curves. The red model has significantly better accuracy, 12% more top 1 accuracy on ImageNet than the green model. The green model is certainly an underdog to this Goliath. However, since it has superb ranking performance, its selective accuracy is better for any coverage below 50%. This means we would, for most coverages, actually prefer the model with a lower overall accuracy. The blue curve is another VIT, and we see that while it has a similar overall accuracy to the red EfficientNet, it is always preferable to use that, the blue VIT. I haven't mentioned VIT by chance. Out of hundreds of architectures we have evaluated, VIT was a clear winner by any aspect of uncertainty estimation that we looked at. So does it mean that transformers or attention are good for uncertainty estimation performance? Well, not necessarily. VIT was one of the first papers to introduce transformers to computer vision. We evaluated 11 additional transformer families, most of which were published after VIT and with the aim to improve it, but all of them had lost its magical touch. Let's look at this graph for an example. The x-axis in this graph shows what is the maximal amount of coverage in percentages that we can get when presenting the model with a constraint for a 99% top 1 accuracy on ImageNet. Please note that 99% accuracy is completely beyond what is currently possible for this dataset. The best models, which are not VIT, can barely provide 30% coverage. Beyond this point, VIT, the red triangles, is the only architecture that can provide more coverage. In fact, it can provide with up to nearly 50% coverage. While the results are not shown in this talk, VIT is also superb at calibration. So you might think perhaps the reason VIT is so good has to do with its large size. This graph measures the model's ranking performance on the y-axis and their number of parameters on the x-axis. We can see that for any category of size, VITs outperform their competition. So if that magical touch is neither attention or size, what is it then? The answer is, I don't know. These questions remain open for future research. We also compare different training regimes and post-training techniques and their effect on uncertainty estimation. Each point in this graph represents the difference in performance between two models of an identical architecture. Therefore, the higher a point is, the larger the improvement by the method it represents. There is a lot of information in this slide we could discuss, but let's focus on the two clear winners in terms of improvement. The first is knowledge distillation, a training regime. Almost all models that are trained with it seem to benefit from doing so. The second is temperature scaling, a post-training method used for improving calibration. Before we move on to very briefly discuss how each method works, notice that temperature scaling has negative improvement for some models, which means it harms them. So let's discuss temperature scaling for a bit. To use temperature scaling, after training a model, we take its output vector before softmax, its logits, and divide them by some scalar t, which we call the temperature. We optimize the temperature on a validation set such that the negative log likelihood is minimized. And that's it. Doing so does not affect accuracy at all, since the maximum label remains the same. Note that while temperature scaling is known to improve calibration, it was not known to also improve selective prediction and ranking. This kind of improvement is not trivial. For example, if we have a generally underconfident model and we increase any confidence score it outputs by some scalar, we might improve its calibration without changing its ranking performance at all. Now, if you remember, we previously saw that some models' selective performance is harmed by using temperature scaling. Well, it turns out that we can easily identify such models. These are models for which the optimized temperature is set above 1, as we can clearly see in the figure at the top of the slide, this figure. Almost any model with a temperature below 1 is improved in terms of selective prediction. This gives us a clear way to determine for which models we should use temperature scaling if we want to improve selective performance. Temperature scaling was originally suggested for calibration. Would we see the same clear division in calibration as well? Well, it turns out that this does not apply to calibration, as we can see in the figure at the bottom. Now, let's briefly talk about training with knowledge distillation. There is a lot to be said on this subject, but due to the lack of time, I will only mention the bare minimum. There are various forms of knowledge distillation, but the one we will discuss is, in my opinion, the simplest version and the one used by most distilled models that we have evaluated. When training a new model, which we call the student, we set another model that was already trained as its teacher. We had another predictive head, a fully connected layer, on the top of the student's model. The student now has two heads. During training, we feed the data to both the student and the teacher. One head of the student is training in a normal manner to predict the ground truth labels and is optimized with a cross-entropy loss. Well, there is nothing special here so far, but the other head is required to try and predict the teacher's softmax predictions and is optimized with a cross-entropy loss according to its teacher's prediction vector. The idea in general, as the name suggests, is to distill the knowledge learned by the teacher into the student. So we observed that knowledge distillation consistently improves uncertainty estimation performance by any aspect. Perhaps we can attribute it to the teacher's uncertainty estimation performance. Well, turns out it isn't the case. In this graph, we see performance in ranking on the y-axis and the performance in calibration on the x-axis. Higher in either of these axes means better performance. So models at the top right corner are the best performance in both of these aspects. The yellow markers represent teacher models and are connected by dashed lines with their students. Student models markers always have a dot inside them and are in colors different than yellow. We see that distillation improves uncertainty estimation in the student even if the teacher is not particularly good. For some of these models, such as the efficient nets and the ECA nets, the teacher was said to be completely identical to the student model with the exact same weights. This means those models had taught themselves, and yet their uncertainty estimation performance improved. Due to the lack of time, I will only briefly mention that we have evaluated all of these aspects in two different settings. The first was uncertainty estimation when the instances evaluated belonged to the same distribution the model had trained on, an in-distribution setting. We call the other setting class out of distribution, which means when the instances belong to classes the model has not trained on. For example, if we train a model to classify different types of dogs, the image of a cat will be class out of distribution. We also developed a novel method to determine how difficult such an instance is to the model and defined different severity levels with which we can benchmark models. This is based on the idea that for a model trained to classify dogs, for example, detecting an image of an airplane as out of distribution is probably easier than detecting an image of a wolf as out of distribution. I will not have time to further expand on this subject in this talk. However, I would like to mention that we have discovered that knowledge distillation is also the best training regime to improve performance in out of distribution, and that VITs are naturally better than any other architecture in this setting as well. These results were only a small fraction of the results we have made. Once the paper is publicly available, we invite you to read it to discover more. While we identified numerous factors contributing to uncertainty estimation performance that were previously unknown, one thing that is missing is an explanation of why these factors are so helpful. Future research will determine why and how these methods could be further improved to enhance uncertainty estimation even more. So, we tried so hard to find ways to improve uncertainty estimation performance. Now let's see how easy it is to completely destroy it. I will now describe our paper, Disrupting Deep Uncertainty Estimation Without Harming Accuracy, that is to be published in EURIPS 2021. This paper presents our novel method for directly and solely attacking the uncertainty estimation performance of deep neural networks. We call our method ACE, Attack on Confidence Estimation. This slide illustrates the operation of the ACE algorithm. Unlike standard adversarial attacks, ACE does not change the model's original predictions, nor does it affect its accuracy. Instead, ACE increases the model's confidence for incorrectly predicted instances and decreases it for correctly predicted ones. In this example, the model predicts that the two original images on the left are tanks. The top one is correctly labeled, and the model is confident about it. The bottom image of binoculars has clearly been incorrectly labeled as a tank, with the model having low confidence in its prediction. To the right, after adding perturbations to the original images, the model has lower confidence in its correct tank label than it has in the wrongly labeled binoculars. Before we delve deeper into the model itself, into the method itself, let's understand what an attacker's motivation may be for using ACE rather than a standard adversarial attack. First, since softmax quantifies the margin from an instance to the decision boundary, we can visualize the predictions of the classifier on a 2D plane where the instances distance to the decision boundary reflect their softmax score. A malicious attacker targeting the classifier has two ways to harm it. The first one is by using a standard adversarial attack, such as the fast gradient sign method, FGSM, or Carolini and Wagner's method to craft perturbation for inputs that have been correctly labeled. These methods, however, have three drawbacks. First, the minimum perturbation required must be large enough to succeed in pushing the correct instance across the decision boundary. The larger the perturbation, the more likely it is to be detected by the victim. Second, even if the attack pushed an instance across the boundary, since the perturbation used is usually the smallest able to do this, the newly wrong prediction is likely to be assigned with low confidence, which might lead the model to abstain from predicting it, therefore diffusing the harm to its accuracy. Third, the victim might be constantly monitoring the model's accuracy, and if it drops significantly, it might indicate an adversarial attack. Since normal adversarial attacks harm accuracy significantly, this will alert such monitors. We present a novel alternative that instead disrupts uncertainty estimation in a manner that does not harm the model's overall accuracy at all. We do this by increasing the confidence for incorrect predictions and decreasing it for correct ones, such that more incorrect instances will be chosen by the model's selective algorithm than correct ones. As we see in the histogram here, incorrect predictions get higher confidence scores than they previously did, and correct predictions get lower scores. This causes the selective algorithm to abstain from more of its correctly predicted instances while providing predictions for more of its incorrectly predicted instances. To apply ACE, we first set an initial magnitude for the perturbation, its rate of decay, and some limit on the number of maximum iterations. Using either the attacked model itself in white box scenarios or a proxy in black box scenarios, we craft a perturbation to push, in this example, a correctly predicted instance toward the decision boundary. If the perturbed instance has crossed the decision boundary, we decrease the magnitude iteratively and try again. If we exceed our maximum number of iterations, we stop attacking this instance since we don't want to affect the model's accuracy and leave the original instance be. Otherwise, we return the first successful perturbed instance. This graph of risk coverage curves showed the damage done by ACE to the selective performance measured by the URC and of an efficient net classifying the ImageNet dataset while using different magnitudes for the perturbations. The blue curve, representing an attack using a magnitude of 0.005, shows that for this magnitude, an end user asking the model for only its 20% most confident predictions will get almost 0% accuracy. Does this blue curve remind you of something? This curve is very similar to a hypothetical curve we saw at the beginning of the talk when discussing the worst possible RC curve. We can clearly see, however, that A succeeds in creating some amount of harm for any magnitude of perturbations used, no matter how small. Note that, unlike any standard adversarial attack, ACE does not only focus on harming the performance of a single instance, but instead harms an entire sample by disrupting its partial order. The last graph was just one highlight of one result from the paper. The paper contains many more results, and we invite you to read it to discover more. In the paper, we also explore other techniques for estimating uncertainty, such as MC dropout and deep ensembles. ACE is the first adversarial attack to target the model's uncertainty estimation performance rather than its accuracy. Note that ACE enjoys two benefits unique to it and not shared with common adversarial attacks. Firstly, the perturbations needed for it are inherently smaller than those needed for most adversarial attacks, since unlike standard adversarial attacks, it avoids crossing the decision boundary. Secondly, its success is not binary. The goal of standard adversarial attacks is to push an input over the decision boundary. If the perturbation magnitude was too small to do this, the attack has failed. In our approach, the attack is partially successful even if it causes a single incorrect prediction to get a higher confidence score than a correct one, with the magnitude of the perturbations only contributing to the potency of the attack by creating a worse partial order and creating a larger confidence gap numerically between the correct and incorrect samples. While ACE introduced a simple, novel way to harm the model's partial order for its predictions, future research could present a more fine-grained method that reverses the original order. Additionally, our results suggest that standard adversarial training does not make the models robust to ACE, and we hope that future work will develop defense mechanisms to protect against such attacks.